Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to continue with the topic discussed in last two lectures. Our topic is the simple harmonic oscillator. So this is our topic. I write continued. So it is in continuation with last two lectures. In the last two lectures, we defined simple harmonic oscillator as an oscillating system consisting of a particle subjective force of the type f of x is equal to minus kx, where k is a constant and x is the displacement of the particle from its equilibrium position. Or we can define it in terms of potential energy. The potential energy corresponding to this force u of x is written as half k x square, right? Then we obtained differential equation for the oscillator, that was d2x by dt2 plus k by m x is equal to 0. Let me name it third. As we have already discussed that this is the equation of motion for simple harmonic oscillator. That is equation of motion. Second order derivative of position function with time plus k by m times the position time function is equal to 0. Then we said solution of 3 is the solution of 3 is, this was the solution, x of t is equal to xm cos omega t plus phi. Let me name it 4, where omega square is k by m. Let me name it 5. I have discussed it already. So this is position time function of simple harmonic oscillator, provided omega square is taken as k by m, right? You can check it. You can check that 4 satisfies 3 provided omega square is k by m. Then we said that xm and phi are undetermined, so they are completely arbitrary. This means that any choice of xm and phi whatsoever will satisfy the equation of motion, that is equation 3, so that a large variety of motions, all of which have the same omega given by equation 5, is possible for the oscillator. And we said that xm and phi are determined for a particular harmonic motion by how the motion starts, right? Then we gave the physical significance of the constant omega. We increased it in equation 4 time by 2 pi by omega, and we concluded that 2 pi by omega is the time period of the oscillator. So we said time period of the oscillator is 2 pi under root m by k, and the frequency, which is reciprocal of time period 1 over t, is 1 over 2 pi under root k by m. So let me encircle them. This is time period, and this one is frequency. Let me name it equation 6, and this is equation 7. So t equal to 2 pi under root m by k is time period, and the frequency, which is 1 over t, is 1 over 2 pi under root k by m. And omega is 2 pi nu, which is 2 pi over t. So then let me name it equation 8. And we named this quantity omega as angular frequency. And we said it differs from the frequency nu by a factor 2 pi. It has the dimensions of reciprocal time, right? Now let us look at the constant xm. Let me use this color. Let us look at this xm. This constant xm has a simple physical meaning. You know, the cosine function takes on values from -1 to +1. Therefore, the displacement has a maximum value of xm, right? And at central equilibrium position x is 0, so its maximum value is xm and its minimum value is -xm. When cos becomes +1, x of t becomes xm. When cosine of omega t plus pi becomes -1, x of t becomes -xm, right? So what is then xm? Xm is the amplitude of motion. So it is simply the amplitude of motion. Right? And you can see xm is not fixed by equation of motion, right? This equation 3 does not fix amplitude of motion xm, right? So motions of various amplitudes are possible, but all have the same frequency and period. So we have a conclusion that the frequency of a simple harmonic motion is independent of the amplitude of the motion. We need to remember it. The frequency of a simple harmonic motion is independent of the amplitude of the motion. Now let us look at this omega t plus phi, or this quantity omega t plus phi, which is the argument of cosine function in x of t, is called the phase of the motion. It is phase of the motion. And constant phi is called the phase constant, right? Now, two motions may have the same amplitude and frequency but differ in phase. To understand it, if phi is minus pi by 2 radians or minus 90 degrees, then what is x of t? X of t is xm cos omega t plus phi. So we put phi equal minus pi by 2 radians. So we will get x of t is xm cosine omega t minus 90 degrees. You know cos theta minus 90 degrees is sine theta. So it is just xm sine omega t, right? So that you can see the displacement is 0 at time t equals 0. See, if you put t equal to 0, sine 0 is 0, x of t is 0. When? When t is 0. Let me write it. So that the displacement is 0 at the time t equals 0. Now, if phi is taken some other value, if phi is 0 degrees, then x of t is xm cos omega t, right? Because it was cos omega t plus phi. We put for phi now 0 degrees. It becomes xm cos omega t. Now, if you put t equal to 0 in this, what you get when t is 0, x of t is xm, because cos 0 is 1. So what is the conclusion? The displacement is xm at t is equal to 0 if phi is 0, because cos 0 is 1. What is the conclusion? Conclusion is the phi decides the initial displacement of the oscillator, right? Where from oscillator starts. If phi is minus 90 degrees, then it is that simple harmonic oscillator which starts its motion at x is equal to 0. And when phi is 0 degree, it is that simple harmonic oscillator which starts its motion at x is equal to xm. Now all values of phi's will correspond to some initial position, right? So other initial displacements I can say correspond to other phase constants. So we need to remember it. Now, the amplitude xm and the phase constant phi of the oscillation are determined by the initial position and speed of the particle. You need to remember these two initial conditions will specify xm and phi exactly, except that phi may be increased or decreased by any multiple of 2 pi without changing the motion. Now, once the motion has started, however, the particle will continue to oscillate with a constant amplitude and phase constant at a fixed frequency unless other forces disturb the system. Now, let us move to V of t. Velocity time function, we know it is time derivative of x of t. So if you differentiate this equation 4 with time, you will get the velocity time function of the simple harmonic oscillator. So I will write it, you can check it. It will be minus omega xm sine omega t plus phi. And we know acceleration is the time derivative of velocity function. So if I differentiate v of t, I will get a of t. It will be minus omega square xm cos omega t plus phi. Let me encircle it. So this gives me v of t. Let me name it. This is equation 9. This gives me a of t, acceleration time function, equation 10. So v of t is minus omega xm sine omega t plus phi, and a of t is minus omega square xm cos omega t plus phi. You can see that velocity and acceleration functions are also oscillating, and the maximum value of the velocity possible is omega xm, and the maximum possible value of acceleration is omega square xm. So this omega xm, maximum value of the velocity, is called velocity amplitude. And the maximum value of the acceleration, which is omega square xm, is called acceleration amplitude. Acceleration amplitude. Omega xm is velocity amplitude, right? Let us move to next thing. Next topic is energy considerations in simple harmonic motion. Let me encircle it. I'm underlining it. Energy consideration, not encircling it. Energy considerations in simple harmonic motion. Now we know its position time function is xm cos omega t plus phi. I will now number these equations again under this heading. I will start from 1. Now we know potential energy of the function is of the oscillator, is half kx square. So if I want the function which gives me dependence of potential energy on time, I have to put x from 1. When I do that, what will I get? I will get half k xm square cos square omega t plus phi. This is I have obtained it using equation 1. I have to just put here x equal to xm cos omega t plus phi and solve. I will get half k xm square cos square omega t plus phi. You can see the potential energy oscillates with time and has a maximum value of this much, half k xm square. So the maximum value of potential energy of simple harmonic oscillator is half k xm square. Let me name it third. So it is proportional to square of the amplitude of the motion, right? Now during the motion, potential energy varies between 0 and this maximum value, as indicated by, I will draw a figure showing this. Let me draw the figure first. So it is energy on this side, it is time on this side. This is 0. That means another color here. This is total energy E. We'll see that total energy is independent of time. Now let me find first potential energy function. It's like this. So let me check it. T here is the period of the motion. This curve shows U of t, right? So the potential energy U oscillates according to this in this fashion. Let me first find the kinetic energy function. Let me name it figure 1. Now we want to find the expression for kinetic energy, which gives us the time dependence of kinetic energy, K of t. We know K of t is half mv square, and we know V is, we have obtained V, time derivative of x. This is our V. I will put it here. So when I do that, I will write directly, it will be half m omega square xm square sine square omega t plus phi. You can see I have written this V. When I square it, minus will go, omega square xm square then will be sine square. You can see I have written same, half m omega square xm square sine square omega t plus phi. But as you know, omega square is k by m from this equation. Omega square is k by m. So I can put that. What will I get? For kinetic energy, I will get half k xm square sine square omega t plus phi. Let me name it. This is under this heading, my equation number 4. So you can see the kinetic energy is also oscillating with time. It is half k xm square sine square omega t plus phi. Like potential energy, it oscillates with time and it has a maximum value of half k xm square, same as the maximum value of kinetic energy. Sorry, potential energy. So the maximum value of kinetic energy is half k xm square. Let me name it phi. Then see that in potential energy function there is cos square, but in kinetic energy function there is sine square. They have maximum values are equal. Both are proportional to square of the amplitude. So let me show the kinetic energy with another color. Kinetic energy will be like this. I'm drawing it roughly. You can understand it. So this is how kinetic energy oscillates with time. Let me check it. Yes, okay. You can see when potential energy is zero, kinetic is maximum equal to total. And when potential energy is maximum equal to total, at that time kinetic energy is zero. Now this line is showing me total energy, which is the sum of k of t and u of t. Total energy doesn't change with time. As we will see, we want to find the total energy of the oscillator. It is simply k plus u, mechanical energy. When you put for that using equations of 4 and 3, 4 and 2, 2 and 4. Using 2 and 4, you will get just half k xm square. Using equations 2 and 4. 4 is for kt and 2 is for u of t. How you can get it? When you sum it, you can factor out half kxm square, and inside the bracket you will have cos square omega t plus phi plus sine square omega t plus phi, and you know cos square theta plus sine square theta is 1. So you obtain this equation. So the total energy is half kxm square proportional to square of the amplitude of the oscillator. I name this equation as equation 6. It is independent of the time as indicated in the figure. It doesn't change with time. This horizontal line shows this key. There is one thing to note, that kinetic and potential energies vary with twice frequency or half the period of the displacement and velocity. Remark. What is remark? We write it in some another color. The kinetic and potential energies vary with twice the frequency, one can say half the period of the displacement and velocity. I repeat, kinetic and potential energies both oscillate, position oscillates, velocity oscillates in simple harmonic motion. But I am saying that the kinetic and potential energies vary with time, oscillate with twice the frequency. Let me underline it. Twice the frequency, or in terms of period, we can say half the period of displacement and velocity. I will not explain it. You can chuck this figure and understand it. This figure 1. So you need to think about it at home. Think about it at home. This is your home assignment. And if we want to find another equation. We know k plus u is half mv square plus half k x square, and k plus u is total energy, so I can write it half k xm square. Kinetic energy is half mv square, potential energy of the oscillator is half kx square, and kinetic plus potential is half k xm square, where xm is the amplitude, right? Now if we solve for v, is the speed, from this equation it will be plus minus square root of k by m times xm square minus x square. Let me name it equation 7. This is my equation 7. Right? When you solve for v, half of will go, you will get k by m plus minus square root of k by m xm square minus x square. Now this relation shows clearly that speed is a maximum at the equilibrium position x equal to 0, and the speed is 0 at the extreme displacements x equal to plus minus xm. Let me write it. Equation 7 shows clearly that the speed is a maximum at the equilibrium position x equal to 0. If when x is 0, this square root will have maximum value, and is 0, that is speed is 0 at the extreme displacements. Extreme displacements means when x is plus minus xm, you put x equal to xm or x equal to minus xm, you are going to get v is 0, because at extreme position the oscillator momentarily comes to halt, it stops, right? This is all for today. Go through all the lectures and make notebook out of it. Don't waste your time, and do not forget to like, share and subscribe my channel. You can comment in the comment box. Thank you. God bless you. Assalamu alaikum.